Hey everyone, welcome back to another deep dive. This time we're tackling something pretty complex, but incredibly cool, deep learning.
Hmm.
And to help us unpack it all, we've got this pretty dense textbook here, all about the fundamentals.
Dense is a good word for it.
Yeah.
Yeah.
So we're going to be focusing on the first three chapters to start, which really lay the groundwork. We're talking about neural networks themselves, how they learn, and some of the tricks to make them even smarter. Sound good?
Sounds great.
Okay, let's dive in. So right off the bat, the book jumps into this whole history of deep learning, talking about these different waves of development.
Yeah, it's like AI has its own version of, surfs up.
Exactly. I love that analogy.
Yeah.
But seriously, though, what's so fascinating is how these waves really reflect like this whole evolution of thinking about AI and the
Mm.
technology behind it.
Definitely. So we start with cybernetics back in like the 40s and 60s.
Okay.
Then we move into connectionism in the 80s and 90s.
Gotcha.
And then finally we arrive at, what we now call modern deep learning, which really kicks off around 2006.
And that brings us to today.
Exactly, and it's still going strong.
It is.
Yeah.
So what's the deal with these waves? I mean, each one kind of builds on the last, right?
Right, but they also like grapple with limitations.
I see.
For instance, those earlier waves, they leaned pretty heavily on unsupervised learning, which honestly had a tough time with more complex tasks.
That makes sense. So this current wave, the modern deep learning era, seems to be riding pretty high. What's keeping it going strong?
Well, one key factor is this shift towards supervised learning,
Okay.
which works way better with those massive data sets we have these days.
Right.
As the textbook actually points out, it's this combo of powerful algorithms and just tons and tons of data that's really fueled this third wave.
So it's not just about the brains, it's also about the brawn.
You got it.
Okay. Speaking of brains, though, how do these neural networks actually mimic the human brain?
So it's important to remember they're not meant to be like these exact replicas of the brain.
Right.
Neural networks are more like a mathematical framework, inspired by the brain's structure and function.
Yeah.
They're designed to learn from data, but not necessarily to like mirror all those biological processes of our own minds.
So they're not going to be writing poetry anytime soon,
No, not yet, at least.
but they can process information and learn, which is still pretty amazing.
It is.
How do they actually do that learning, though?
That's a great question.
It's not like we can just download information into their brains like we do with software right away.
Definitely not. That's where optimization comes in.
Optimization.
Yeah. Think of it like trying to find the lowest point in a valley.
Okay.
You could wander around aimlessly, or you could follow the slope downwards, right?
Right.
So neural networks, they use a method called gradient descent,
Gradient descent.
which basically means following that steepest path down towards the minimum of what we call the loss function.
The loss function.
Yeah.
Is that like a measure of how lost the network is?
That's a good way to think about it.
Like how far off it is from the right answer?
Exactly. The loss function tells us how well the network is performing,
So the lower the loss.
the better the predictions.
Makes sense.
And gradient descent, that helps the network adjust what we call its parameters. It's like the internal settings of the network to gradually minimize that loss and get closer to that correct output.
So it's a self-correcting system.
Kind of like that, yeah.
Cool. But I'm guessing it's not always a smooth ride down into that valley. What are some bumps in the road these networks might hit during this whole descent thing?
Well, one challenge is getting stuck in what we call local minima.
Local minima.
Yeah, it's like thinking you've hit the bottom of the valley, but there's actually a deeper point somewhere else.
You just don't see it.
Exactly. So the network kind of settles for a decent solution, but it's not the best one.
So you can't win them all.
Yeah.
Are there other challenges they run into?
Oh, definitely. Especially with really deep networks, we can run into something called vanishing or exploding gradients.
Vanishing or exploding gradients. Okay. What does that even mean?
So gradients, those are what guide the adjustments we talked about.
Yeah.
Sometimes those gradients either become super tiny, that's vanishing,
Okay.
or they blow up to these huge numbers.
Exploding.
Right. And that can really mess with the whole learning process.
So it's like we need to give these networks a good set of breaks.
Pretty much.
The textbook mentioned something called momentum as a way to kind of handle these issues. Does that sound familiar?
Momentum, yeah. It's a technique that helps smooth out the learning process.
Okay.
Imagine a ball rolling down a hill.
Okay.
Momentum helps it keep its speed and avoid getting trapped in those little dips along the way.
Right.
It's like giving the optimization algorithm a little extra push in the right direction.
So it's all about finding that balance.
Exactly. Balance between making progress but not veering too far off course.
This is getting pretty complex.
Yeah.
And I feel like we've only just scratched the surface.
Yeah, deep learning is a deep topic.
What's next on the agenda for our deep dive?
Well, now that we've got a handle on neural networks and how they learn through optimization,
Right.
we're ready to tackle regularization.
Regularization.
Yeah.
Okay, so regularization, it sounds kind of like we're giving these neural networks a personal trainer.
Yeah, that's actually a pretty good analogy.
Really?
Regularization, it's all about preventing those networks from getting too fixated on the training data.
Right.
You want them to learn these general patterns, not just memorize, the specifics of the examples they've already seen.
So like making sure they're not just cramming for a test.
Exactly. You want them to understand the material deeply.
Right. So how do we stop them from just becoming these overconfident crammers? What kind of training regimen does regularization involve?
Well, there are a few techniques. One common one is called weight decay.
Weight decay.
It's kind of like adding a penalty for having these overly complex explanations.
Okay.
So if a network relies too heavily on any one feature weight, decay basically nudges it to simplify its approach a little.
Keep it concise and to the point. Got it. Are there other techniques?
Yeah, definitely. Another powerful one is called early stopping.
Early stopping.
Think of it like baking a cake.
Right.
You don't want to leave it in the oven too long or it'll burn right.
Right.
Same idea here. If you train a network for too long, it might start overfitting to that training data.
So we're looking for that perfect cake, golden brown, and ready to generalize.
Exactly.
But how do we know when to pull it out of the oven, so to speak?
Well, we keep an eye on how it's performing on what we call a separate validation set.
Validation.
This is kind of like our taste test.
Okay.
It makes sure the cake isn't just appealing to our own, biased palate.
Right.
If the network starts performing worse on the validation set, even though it's getting better on the training set, that's our sign. It's time to stop.
So it's all about balance again, learning from the data, but also avoiding those pitfalls of overfitting.
Exactly. And regularization, that's a crucial part of achieving that balance.
It sounds like it. Okay, I have to admit my brain is starting to feel a little full after all of this.
Yeah, it's a lot to take in for sure. We've covered a ton of ground in these first 3 chapters.
We have.
But these foundational concepts, they're essential, for understanding the power and potential of deep learning.
They really are. Okay, before we wrap up, there's one thing that's been bugging me.
Okay.
The book keeps mentioning representations of data.
Right.
And how that can really affect a network's ability to learn.
It's a big deal.
So what exactly does that mean? Representations of data.
So representations, they're essentially how the data is presented to the network.
Okay.
Think of it like the difference between trying to learn a song by listening to it versus trying to learn it by reading sheet music.
Okay, I see. So the same information,
It's all there,
but presented in different ways.
and that can make a huge difference in how easy it is to understand.
Right. So the right representation can make learning faster and more efficient.
Absolutely. And the textbook actually has a great example of this.
Oh, yeah.
Figure 1.1, it shows 2 different ways to represent the same data.
Okay.
In one representation, it's almost impossible for a simple linear model to separate the 2 classes. But in the other one, the separation becomes super obvious.
Wow. So the way we represent data can actually make or break a model's ability to learn.
It really can. It's pretty powerful.
That is powerful.
And it highlights this importance of understanding not just the algorithms, but also the data itself.
Yeah.
Getting that representation right, it's often the key to unlocking the true potential of deep learning.
Okay, well, I'm definitely feeling much more enlightened now about the importance of data representation. It's like choosing the right tool for the job, I guess.
Yeah.
But speaking of tools, the textbook also hinted at some pretty serious math being involved in deep learning.
Oh, yeah.
Is that what's coming up in the next chapter?
You bet. We'll be diving headfirst into derivatives.
Derivatives?
And how they actually power those optimization algorithms we've been talking about.
Buckle up, everybody.
It's going to get a bit technical, but I promise it'll be worth it.
All right, deep divers. Get ready to flex those math muscles. We're about to go even deeper into the inner workings of these networks. Okay, so we're back. Ready to tackle those derivatives. I have to admit, I'm a little rusty on my calculus, but I'm curious to see how it all ties into deep learning.
Well, derivatives, they're all about understanding change.
Yeah.
In deep learning, we use them to figure out how, like tweaking those network parameters, remember those?
Uh-huh.
How those tweaks affect the performance. It's like fine-tuning a recipe.
Okay.
A little more of this, a little less of that to get the perfect outcome.
So we're using calculus to bake the perfect neural network cake.
I like it. That's a good way to put it.
But can you give me like a more concrete example?
Yeah.
How do derivatives actually come into play here?
Sure. So remember the loss function.
Yeah.
Tells us how far off our predictions are from the real deal.
Right.
The derivative of that loss function, that tells us which way and how much we need to change those parameters to get that loss down. It's like a compass,
Okay.
pointing us toward better performance.
So the derivative is our guide on this optimization journey.
Exactly.
Now, the book also mentions second derivatives. Why do we need those?
Second derivatives. Those give us info about the curvature of the function.
Converture.
It's like knowing not just the slope of the hill, but how steep it's getting.
Okay.
This helps us fine-tune our steps, avoid overshooting that minimum of the loss function.
So, second derivative, it makes sure we don't take giant steps and end up on the other side of the valley.
Exactly. It's all about balance. Smooth, controlled progress toward that best solution.
This is starting to make sense.
Yeah.
But I have to say, deep learning feels huge. And we've just dipped our toes in.
Yeah, these first 3 chapters are really just the foundation. There's a whole universe of concepts and techniques and applications out there.
It's a little daunting, but exciting at the same time.
It is, and that's what this deep dive is all about. Sparking that curiosity, giving you a solid base, and then you can explore on your own.
Well, mission accomplished, I think. Thanks to our deep dive here, I feel like I've got a much better grasp on these fundamentals of deep learning. I'm ready to tackle those next chapters.
That's great to hear. And remember, deep learning, it's always changing. But these core ideas, those will stick with you.
They will. And to everyone listening, thanks for joining us on this deep dive into the world of deep learning. We hope you learned something new. And until next time, keep learning, keep exploring, and stay curious.